Yeah, hello and welcome to our webinar. The topic today is active versus passive cooling systems of inverters. My name is Volker and I'm your trainer today, and I've got here with me Roland. He's in the chat room, so whenever you have questions during the webinar, feel free to type in your questions into the question window, and we'll answer that questions immediately, or if it's something interesting to all of us, then we can do also, we handle these questions at the end of this webinar. All right, so the topic today is basically why is active cooling the better technology for power electronics or for inverters. So, and before we go into the question or answering this question, I want to define basically what are we talking about here. So active cooling system. Whenever we have got a fan inside the inverter, then we can talk about that's active cooling. But actually, to be precise, we have to say we have usually like two fans. So there's one fan inside the inverter that basically circulates the air inside to prevent hotspots, and another fan that is basically just cooling the heatsink. Usually it is the way that the outside air does not get into the inverter. So their PC boards never get in contact with moisture or dust or whatever, because it's hermetically sealed. And via this heatsink, you basically cool only the heatsink with the main fan, and that's typically the design of active cooling. So passive cooling is a little bit different. Passive cooling is like similar like a convection cooling. I mean, there's all types of designed convection cooling as well. So you have got, for example, chimney effect or something like that. So what you can see here, for example, in the picture on the right hand side, there's natural convection. So it's kind of a radiation and without any chimney effect or anything like that. But usually there is no main fan with passive cooling involved. Nevertheless, it can be still a fan built inside the inverter to circulate the air inside, also to prevent hotspots or like local hotspots. So, but in general, I would say Fronius is using active cooling pretty much all the time, and the reason why we believe active cooling is the better technology is here. So let me sum it up first, and then we go into details. So active cooling means less costs, basically, because we're not just looking here at the initial cost of inverter. Usually with Fronius, we always look holistically on the total costs of a PV system, for example, over 10 years, 15 years, or 20 years. Then we also expect more yield or better performance with an active cooled inverter. Active cooled inverters also have usually the advantage that they are, from terms of the weight, they are easier than others, and they are more flexible. And one main argument, I would say, is the longer lifespan. But let's look now into details of these arguments. Active cooling can mean more flexibility. So you have basically no restrictions in the way how you mount the inverter on a wall or a roof. So from a horizontal mounting to a vertical mounting and all angles in between is possible, so there's no restriction. But with passive cooling, usually they need to be mounted 90 degrees vertically only, because with these the certain effects what you need to create, like this chimney effect of connection cooling. It is really important to mount it vertically, otherwise the cooling wouldn't work, and that has of course an impact to the inverter. Yeah, the active cooling inverters sorry, have a longer lifetime, and like in general you can say that basically applies to all electronic parts and power electronic. The hotter power electronic parts get, the shorter the lifespan. And this is also, for example, applies to like a normal laptop or like a mobile phone. So if the CPU, for example, it gets very hot, that has an effect on the lifetime. And there is actually a detailed formula behind that. And that is if you increase the temperature by 10 degrees, then that can cut the lifespan of an inverter or power electronics by half. And I would say that is a really strong argument, because imagine you have got an inverter in the typical surrounding where you've got 25 degrees. That has very much a difference in the lifetime. For example, if you have got an average temperature of 35 degrees, only 10 degrees more. Or imagine you all have got, because it's a hot day, because it's mounted on a wall outside, for example, and you have maybe a bit of a heat situation where you have got more than like a normal hot day. The ambient temperature, like 45 degrees or even 50 degrees in the surrounding, that cuts the lifetime then to a quarter or even more. So, I mean, of course, this is not a linear effect, but it's actually more like towards like exponential. But it also depends what exact temperature we are looking at. But in general, like the point what we want to make, you know, you have got this situation, you can't get the heat away with passive cooling, and that's like as easy. And 10 degrees only, like, do you really want to risk, you know, to shorten the lifetime by half? Like, this is like we really want to point out. Yeah, active cooling can we say has less means less stress on the electrical components, and therefore longer lifetime, and with passive cooling temperatures. Okay, turning to another argument is about the yield. Basically, you can also say once you expose an inverter to high temperature, you have the situation that the inverter would ramp down its output power to basically make sure that it doesn't break down or nothing gets broken. And what the effect is out of that is you can have a negative impact in your yield. And active cooled inverters usually have a better power derating because of the behavior that the cooling effect is much stronger. You have basically the opposite with passive cooling, because you're easily in the power derating mode. So yeah, in particular when you have got when you are from countries with warmer climates and you mount them outdoors, then it can be, in particular in summer, that you have got power derating. And we actually looked at the rating curve of some other competitors, and yeah, what I wanted to show here is like in blue we have got a competitor here, and in red is a comparison. We've got the Fronius derating curve, and if you look here, that you will find that a competitor has power derating already from 30 degrees onwards, versus Fronius is at least 10 degrees higher. But that can really make the difference, as I said, right? And imagine, for example, you have got the situation here in this situation where I've got like 40 degrees, maybe because it's mounted outdoors somewhere, then you have only 80% of the output already, which is a very strong impact, I would say. Yeah, but of course this is a theoretical thing. So for me it was the question like, so how would this look like with a real installation? And therefore I looked at an installation what one of our customer has. It's a 100 kilowatt system, like 100 kilowatt DC, mounted on the roof, and there are 5 Fronius SIMO inverters connected to. So there are actually 4 SIMO 20s plus 1 SIMO 10, so it's 90 kilowatt AC in total. And what you can see here is a picture of our monitoring system. So these are real data. And the blue curve, what you can see here is the ambient temperature, which we're also recording. First of all, you can see there is no dint on the top of the curve, so that means none of these inverters are derating. Even though the outside temperature, what is measured here, is actually exceeded 50 degrees, which is already quite high temperature. Nevertheless, so with active cooling, you see there's no power derating. So the question was like, how would it look like then with passive cooling? And these are these points which we calculated here. So if you basically use the derating behavior from the inverter what we looked beforehand, your output curve or output of the inverters on this particular day would look like this. And as you can see here, it's actually a significant reduction in the output power. And on this day, you would lose what we calculated of approximately 96 kilowatt hours, and that is an equivalent of around 15%. So if you imagine, you know, when it's during the summer where you have most of the time your main yield of a PV system, but at the same time in this system you would also have like the biggest losses, and like 15%, that's actually quite something. And I would say it doesn't matter if you have got a passive cool inverter and has 0.3 or 0.5% more maximum efficiency. But if I look at 15% you know, losses due to power derating, that's way stronger than the efficiency of an inverter. So this is one of the main reasons why we believe the active cooling is the better technology. Let me now turn to another argument, that is the maintenance. Active cooled inverters are usually maintenance free. So that means if we look at 10, 15 or 20 years lifetime of the PV system, then usually there are no costs regarding the maintenance for the cooling. Of course, if you are living in the desert or you have got for some reason extremely high conditions, like strong conditions with dust and sand maybe, then this is of course an exception. But I would say under normal conditions, if you live in a city, if you live in the countryside, of course if you mount it inside, usually that's what I could call the normal conditions, and then it's maintenance free. With passive cooling, you need to remove the dust. Usually the housing of the inverter is at the same time the heatsink, or it's on the back, depends how the inverter is designed, of course. And for example, what I've got here, I've got the manual from a from a competitor, and they state that you have to clean the inverter every 6 months. So twice a year you need to clean. And if you think of, in particular, of commercial installations where you've got multiple string inverters, for example, then you really need to make sure that you get the return of the investment of this commercial system. Or if you you really want to gain, you know, the interest from the PV system, then it's very important to look at these costs. And twice a year, over, let's say, 10 years, 15 years, again, that can create some high costs. And this is what people sometimes do not think of. Of course, it always depends which country you are and what you pay for the maintenance, but I would say this is also a strong cost argument. And if you think further, the question is, like with passive cooling, so we've seen, you know, the temperature derating behavior, and we've seen what maintenance is required. But what if insufficient maintenance and high temperatures come together? Right? You can basically imagine that you have got even higher losses than what we've seen before in this derating curve of the inverter. It's always hard to say, of course, how strong the derating with polluted inverter or with like dust which was settled on the inverter or in the cooling heatsink, but because it depends what kind of dust it is, you know, what the source of dust is. So there is dust that is a bit more insulating, then there is dust that can act like a bit more, preventing heat insulation. That's why it's very hard to say what exactly it will look like, the temperature derating, but just to give you the idea that it's not just about isolatedly looking at these arguments, it's also about you know, a combination that can happen. Yeah, that's actually already basically it with what I wanted to tell you today. We've basically seen that we've got less costs because no maintenance or low maintenance costs, no extra costs for cleaning an inverter, so that's why less costs on the long run. We've seen there's possibly more yield because of the better performance, like derating, power derating from an active cool system is way higher usually than like passive cool inverters. We can also say that they are easy to install because simply the inverters is a lot more lightweight. We've seen that it's flexible because of you know, you have no restrictions in which angle you want to mount the inverter. If you have the requirement, you have to put it somewhere, even on the roof or so, you can do that. And I would say a very strong argument is the lifespan, because if temperature gets higher, then you can have a limitation in your lifespan. So that's all I wanted to mention today. I can also see that we've got some questions in the meantime. And we've got someone, let me double check. Can inverter with active cooling really achieve IP66? So yeah, this customer is referring to the IP protection class. With IP66, Fronius Simo eco inverter is has IP66, which is the highest IP protection which you can get on the market. And yes, you can achieve IP66 because the definition of the IP protection class is, as always, what is the weakest point of the inverter. And since the fans what we are using are IP67, so that means this fan could actually even run temporary underwater, so that's protected quite well, I would say. So yes, IP66 is still possible. Then we've got another question. Do the fan need maintenance? I think I mentioned that already a little bit in the presentation. Basically the fans or the whole inverter is designed for a lifetime of 20 years. So within that period of time, it's not necessary to maintain, or let's say to change in a fan or anything. Usually not. So they should last for that time. And also, yeah, another question which is referring to the MTBF, which is like the mean time between failures of fans. I also want to explain a little bit on this. So I don't know for you guys if you know MTBF, that's a measure which means mean time between failures, which is actually, well, some people use it for predicting how long a power electronic will last. We do not really rely on these things actually, because it has nothing to do, this number has nothing to do with reality. Mean time between failures is basically a mathematical formula, I would say, which is the combination of the likelihood of the breakdown of single components inside the inverter, which is only a mathematical number which has nothing to do with the reality. So the better question would be, so what is the failure rate? Usually also when we talk about failure rate, it makes a difference whether you talk about an inverter which is on the market for, let's say, a year, so quite new on the market. And of course you can expect the failure rate of an inverter which is 1 year on the market is actually pretty much zero, I would say. Versus if you got inverters 20 or 25 years on the market, which was what Fronius has, for example, then you can say at some point in maybe 30 years time we'll have 100% failure rate, right? So when we talk about a failure rate, it always needs to be said, so what period of time are we talking about? And this is often not said when we talk, or when someone is talking about the failure rate, in general, we have what we see in the lifetime of our inverters, let's say with the snap inverter range, with our newest, that we are in the thousandth of failure rate, so extremely low. We're not using, or let's say we're using fans that are commonly used, not just inverters, they are also used in cars, in several other power electronic devices. So this is nothing particular for inverters. They are very well developed and very well designed and tested. Okay, yeah, that's so far with the questions. We are still available for your questions. If you have some, just type it in or email us after the webinar. So that's it from our side, and I would say thank you for your participation, and yeah, talk to you next time. Bye bye.